Good day, viewers all over the world. You are welcome to Toydale online class. Today we want to talk about, we are starting with partial derivatives. So what do we understand by partial derivatives? The partial derivatives are the rate of change with respect. The partial derivatives are the rates of change with respect to each variable separately. That is, when we have f of x, if you have f of x, the derivative of this is f prime of x. Okay, that is, this simply means df dx. This is just the total derivative. But if we talk about the partial derivatives are the rates of change with respect to each variable separately. So that is what we know. We understand by partial derivatives. For instance, if you have two variables, x and y. If we have two variables, x and y, say f of x comma y. So here we have two variables. So what do we do? How do we find the partial derivative? It simply means that if you are differentiating x with respect to x, this will be the half the x. That is, we are taking the first one, the half the x. Then if you are differentiating f with respect to y, that is where we have x comma y, this will be the f the y. So we are talking about partial derivatives in this sense. Okay, this is the half the x, and this is the half the y. So when we have partial derivatives, partial derivatives are the rates of change with respect separately. Other derivative of the variable. In this case, there are two variables, x and y. In this case, we differentiate f with respect to x partially, and here we differentiate y. We differentiate f with respect to y partially. So that is just simple introduction to partial derivatives. And of course, we can have more than two variables. We can have f of x, y, and z. In this case now, there are three variables. So when we have three variables, we can actually differentiate f with respect to x, we can differentiate f with respect to y, then we also differentiate f with respect to z. So let's take notes that under partial derivative, the rates of change with respect to each of the variables separately. So let's take notes. I want us to take notes. So I will now give example to buttress my points on the partial derivative. For instance, let's take example. Let's take example 1. If we are to compute example, let's say compute the partial derivative. Let me abbreviate partial derivative as PD. The partial derivative of, we have f of x comma y is equal to x squared y cubed. Okay. In this case now, there are two variables here, x and y. So we want to compute the partial derivative of what we have on the board. Of course, the first one is when we differentiate f partially with respect to x, the half the x will now be under partial derivative. What we want to consider in this case now is derivative of f with respect to x. So we pretend as if y is a constant. So if you do that here, if you differentiate f with respect to x, this will be 2xy cubed. That's what we are going to get. That's what we are going to get. Then we can also differentiate the f, the y. We can differentiate y partially with respect to f, partially with respect to y. And that is going to give us 3x squared, y squared. That's what we are going to get. If we differentiate f partially with respect to y, that's what we are going to get. So that's what we are going to get there. That's what we are going to get. And of course, we can go ahead and differentiate the second time. That is, we can also have the square f all over the x. You know this is the x. I can from this result now, I can go ahead and differentiate again with respect to y. That is the f, the y. And that will be, if I do that, I'm going to have 6x y squared. So also, we have differentiated f partially with respect to y before. Then I can differentiate the result again with respect to x. That's now the square f all over the y, the x. And that will be, we are differentiating with respect to x now. That will be 6x y squared. Okay? 6x y squared. But we should note that what we have here is the same thing as what we have here. So before we take the next example, I'm going to give the theorem that back this up. That is, if we differentiate partially with respect to x, then differentiate partially with respect to y, it's the same result as when we first differentiate partially with respect to y, then with respect to x. So let's take notes. So I'm going to give this the theorem that guaranteed what we have there. Then we can also say that we can have the square f all over the x squared. We can have that, the square f all over the x squared. And if we do that, that's going to give us, when we differentiate this again with respect to x, that will be 2y cubed. We can also differentiate the square f all over the y squared. That is, we can have the square f all over the y squared. Let's differentiate by the second time. That will be 6x squared y. So please let's take notes that under partial derivative, the partial derivatives are the rates of change with respect to each of the variable separately. So let's take notes. Let's take notes. So we can be asked, when we are given a function that contains two or more variables, we can actually differentiate partially. So let's take notes. That is that about first example. No, I made a statement here that the square f all over the x, the y is same thing as the square f all over the y, the x. So the theorem that guarantees that is what we are about to discuss before we take any further example. And we should note the theorem very well. The theorem is important. Let's take note of the theorem. And the theorem is called the Clairaut theorem. This is the theorem that guarantees the statement that we make the other time. That is the theorem. So the theorem says that suppose, this theorem is important, suppose that f is defined. Suppose that f is defined on a disk D that contains the point A, B. So if the functions f subscript x and y and f subscript y and x are continuous, if the functions are continuous on this disk, then f s y into bracket a comma b will be the same thing as f y s into bracket a comma b. So what is the implication of this theorem? This theorem actually guarantees that when we take the partial derivative, the theorem says that suppose that f is defined on a disk D that contains the points, these points A and B. So function f cosecant y, that simply means that the partial derivative of x, we first take the partial derivative of x with respect to the partial derivative of f with respect to x, then we take the partial derivative of f with respect to y. And if we first take the partial derivative of f with respect to y, we later take the partial derivative of f with respect to x are continuous on this disk, then this result holds. So please take note, under partial derivative, when we find the square f all over the x, the y is same thing as the square f all over the y, the x. So this is the theorem that actually guaranteed that analogy. So please let's take note of this theorem, it's important. So in some questions we can be asked to state this Clairaut theorem. You can be asked to state this theorem without proof. So it's important. Let's take note. Let's take note. It is very important. So that's not about that. So we take the second example. Let's take the second example under partial derivatives. Let's take another example. Let's take another example under partial derivatives. So example 2. Example 2, where we are asked to calculate the second order partials of f of x comma y to be equal to x cubed plus y squared ex. So we have to find the second order of this problem. And of course, the second order of this problem will actually be, we first find the first order before we go to the second order. That is, if f of x comma y is equal to x cubed plus y squared e raised by x, then the x, which is the first order partial derivative, when we differentiate this with respect to x, we are going to have 3x squared, then plus y squared ex. That's what we are going to get. Of course, we can have the y. If you have the this one does not have y. So this will be 2y e raised by x. So the second order partials now will now be the square f all over the s squared. We can have the s squared. So this is going to give us, when we take the second derivative, it will be 6x plus y squared ex. That's what we are going to get. Okay. Then we can also have the square f all over the y squared. Okay, when we differentiate this second time, it will be 2y e raised by x. It will be 2e raised by x. So we can also go ahead to actually prove the theorem that we stated the other time. Then if we do that, let me just clean the second one. Oh, I can write it here. We have the square f all over. We've differentiated f with respect to x. Now let's differentiate second time with respect to y. We have the x, the y. That is this result. We want to differentiate this result with respect to y. Of course, this one does not contain y, so we're silent about this. We go to this place. This will be 2y e raised by x. Then let's come to this place. The square f all over the y, the x. The y, the x. This is going to give us 2y e raised by x. Let's take note that we should take note that by that theorem, the square f all over the x, the y is same thing as the square f all over the y, the x. So please let's take note. It is very important. So that Clairaut theorem is very important. So let's take note. Let's take note of the theorem. So I would love to stop here. We continue from there in our next class. Thank you.